Hello again, everybody, and here we are, the third part of Chapter 7, Independent Samples T-Tests. I think you'll see that at this point we're following pretty much the same format that we have in the past, and by now I'm hoping that you're sort of seeing the way that we progress through a hypothesis test and the steps for a hypothesis test using t-tests. So just to review where we are, we started Chapter 7 looking at one sample or single sample t-tests, and in that case we had one sample. We knew the population mean, or we had a pretty good estimate of the population mean. We took one sample from the population and treated that sample, and then compared the sample mean to the population mean. In that case, we only had one sample. Last week we did paired samples t-test. In this case, you had two samples that were the same participants. So the same people before and after a treatment typically is the way that we do a paired samples t-test. The key is for a paired samples t-test, the two groups are the same people. I may have mentioned you could also do a matched participants design, but for the purposes of this class, we'll talk about paired samples being two groups of the same people. And then today we're talking about an independent samples t-test. In this case, you've got two samples that are different people, and that's the key. You've got two samples filled with totally different participants. Okay. So, an independent samples or independent measures design allows us to look at differences between two separate samples. And in your final project, which is coming up now at this point, we're about halfway through the semester, or in the final exam, if you were trying to figure out if you were supposed to do an independent t-test or a paired samples t-test, is basically if you have two separate or independent samples, meaning that the people in the two groups are different, you're doing an independent measures t-test. Whereas if you have two groups, but the people in the groups are the same, so we're looking at the same people before and after a treatment, then you'll be doing a paired samples t-test. So an independent sample or an independent measures design, an independent samples t-test, is looking at mean differences between two different groups. So you could compare men versus women, right? Those are two groups of people. You would have different people in each group, and you could compare men versus women on statistics ability. Maybe we're interested, is there a gender difference in ability to do statistics? So we would recruit one group of men and one group of women, give them each the same statistics test, and then compare them. In this case, you've got two groups, one with men, one with women, and there are different people in each group. Therefore, you have an independent samples t-test. Or you could look at two different treatment conditions like drug versus no drug, maybe on symptoms of attention deficit hyperactivity disorder, ADHD, and we have one group of children who are taking some kind of medication, one group of children who are not taking the medication. We have different people in each group, and then we look for symptoms of ADHD as our dependent variable, as our measured variable, and compare the two groups. So the people in one sample are different than the people in the other. We would say that the samples are independent, and therefore you would do an independent samples t-test. So the independent samples design is used where you have no knowledge about either of the two populations, meaning you don't know anything about population means or population standard deviations. So the population means and standard deviations are unknown. All we are doing is comparing one sample mean to the next sample mean. And as with all of our hypothesis tests, the general idea is that our independent measures or independent samples t-tests will determine whether the mean differences that we see in our sample are what we would consider to be real differences that we would think we would see in the populations, or if the difference between the two groups is simply a result of sampling error. Remember, we're using samples, independent samples, t-test. So we use two samples, and we're getting a mean. Let's say we're looking at symptoms of attention deficit hyperactivity disorder. And we will use our sample to say something about how this new medication works in the population. We only care about our samples insofar as they tell us something about the population. We use our sample data to estimate what we think is happening in the entire population of all children who are diagnosed with ADHD. And so our question really becomes, is the differences we see in our samples, let's say the children who were not taking the medication showed more symptoms of ADHD, so they're more hyperactive, more impulsive, more fidgety, harder time sitting still, compared to those who did take the medication. And then we want to see, do we think that sample mean difference would hold up in the population if we gave this medication to all children who were diagnosed with ADHD? Would we still see that symptoms of ADHD would decrease? Or do we think the difference between the symptoms of ADHD in our two groups is so small that it's probably not a result of the medication, but just the result of sampling error? So with an independent samples t-test, you're really interested in the differences between the means of your two samples, and the question becomes, how extreme is the difference between the two means? So if you have something like this, here are two samples. Let's say, I'm looking here, the control group is lower. So let's say this is a treatment for memory. We are going to teach people some memory tricks that we think will improve their memory. And so we have two groups. We've recruited two groups of totally different participants. Let's say we've got 50 people in our control group and 50 totally different people in our treatment group, which is this blue curve. And we give everybody the same memory test. So the control group takes the memory test. Not everybody gets the same score, right? There's variability. This is basically a histogram, which at the bottom here would be memory scores, and this y-axis would be frequency. And so we've got most people in the control group with a memory score around here, that would be the mean, and some people over here a little below and some a little above, but generally this is how the group performed. For the people in our treatment group, let's say we picked 50 separate people to be in the treatment group. We taught them this new memory technique, and then we gave them the same memory test. And what we see is that the blue group, or the treatment group, their mean is higher than the control group, meaning they remembered more items than the control group. Again, not everybody scored at the mean. We have some people scoring up here, higher than the mean, some below the mean, and generally this is where they performed. The question for an independent samples t-test is this difference between the mean of the control group and the mean of the memory group in our samples, right? These are 50 people in each group. So these 100 people, the difference in the mean of the control group compared to the mean of the treatment group in our sample. Do we think we would see that if we tested the whole population? Would we see this increase in memory using our memory technique? Or is the difference between these means so small that it could likely be sampling error? that actually our memory technique didn't work and this is just error. And that if we took another 50 people in the control group and 50 people in the treatment group, we wouldn't see this at all. Or we might see that the two means are the same, and that this is just, what we're seeing in this sample is just sampling error. So, our hypothesis test follows a similar procedure that we've used for the other tests that we've done. For this example, I'm going to look at two groups of children, one group whose parents are married and one group whose parents are going through divorce. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 children whose parents are married and 10 children whose parents are going through divorce. Notice these would have to be two separate groups of people, right? We don't have the same children in each group. They're different children. And the scores here are scores on what we're going to call a physical health score, PHS. And we're kind of curious in this study is parents' marital status, whether your parents are married or whether your parents are going through divorce, does that affect children's physical health? We know there's some relationship between mind and body. So if you're maybe stressed out because your parents are going through divorce, does that result in children having more physical health issues compared to children whose parents are married? So that's what these scores are. This is some kind of questionnaire parents fill out, and we're looking at physical health scores comparing children whose parents are married to those whose parents are going through divorce. This is made up data. This is just as an example. Because we have two groups of participants, two samples, and they are different people, we know we'll be doing an independent samples t-test. So the populations that we're interested in, the independent variable and the dependent variable, and how do we choose our statistical test? If you've been feeling pretty good about the idea of independent variable and dependent variable, pause here and see if you can figure out what the answers here would be. So the population that we're interested in are all children whose parents are married, that would be our population 1, compared to all children whose parents are going through divorce, that would be our population 2. We're comparing two different populations or two different groups of individuals. The independent variable, our treatment variable, is parents' marital status, and we have two levels. We've got parents whose children are married and parents whose children are going through divorce. And our dependent variable is this physical health score, PHS. And as I said, we'll be doing an independent samples t-test because there are two separate groups with different people in each group. All right, so step 1 is always to express our hypotheses in symbols. And by now, this might look a little bit familiar. Our null hypothesis, the hypothesis of no effect, is that the mean physical health score for the first group should be equal to the mean physical health score for the second group, meaning that parents' marital status has no effect on physical health score, right? That's the null hypothesis, that the independent variable has no effect. And so if the independent variable has no effect, then the mean physical health score for children whose parents are married should be equal to the physical health score for children whose parents are going through divorce. You can write your hypotheses either way. This first one I have here is using symbols. mu1 is equal to mu2. And in this case, mu1 is married, mu2 is going through divorce. Or you can use a more descriptive subscript there. So the null hypothesis would be mu of the parents who are married, children whose parents are married, is equal to the mean physical health score, or mu, of children whose parents are going through divorce. I kind of like using the more descriptive subscript so that you're kind of clear of what you're talking about versus just the numbers, but it's truly up to you. And in words, we're saying the mean physical health score of children whose parents are married will be equal to the mean physical health score of children whose parents are going through divorce. And you can write it this way or with the numbers as subscript. You don't need to write both. You just pick whichever way you like better. And then the alternative hypothesis here is that mu1 is not equal to mu2. Remember, for the alternative, we're assuming that the independent variable does have an effect. And in that case, we're saying that the mean physical health score for children whose parents are married, I'm using the second one here, would not be equal to the mean physical health score of children whose parents are going through divorce. So it's the same with just the not equal sign for the alternative hypothesis. Step 2 is running your statistical analysis, and we'll do that in my SPSS lecture, but it's pretty simple. One thing to keep in mind, your setup of your data looks different if you're doing a paired t-test versus an independent samples t-test. If you're doing an independent samples t-test, you need one column with your independent variable, which is this parent's marital status, and I've got 1 as children whose parents are married, and 2 is representing children whose parents are going through divorce. And then my second column is the physical health score, or the dependent variable, and so my first participant whose parents are married, their physical health score was a 77. My second participant whose parents are married, their physical health score was 88. You go through that with all of your children whose parents are married, and then we start here on line 11. This is a child whose parents are going through divorce, and their physical health score is 87. This person is the next person whose parents are going through divorce, and their physical health score is a 77. So you have 2 columns. The first one has your independent variable, or it doesn't matter which order it's in, but one column has the independent variable, one column has the dependent variable. And you may want to look back at your paired samples t-test. When you do a paired samples t-test, you have 2 columns, one with scores at the pretest, one with scores on the post-test. So row 1 in that case, if this was a paired samples t-test, would be the person's pretest score here and the person's post-test score right next to it. And so each person has their own row, and they have 2 scores on each row. In this, and for an independent samples t-test, you've got 2 columns as well, one with the independent variable, one with the dependent variable. So how you set your data up in SPSS is really important, and you'll want to consider that, again, especially going into the final project. Okay, next is to get our output and see what it means. So here's our independent samples t-test outcome, or output from SPSS. Up here we've got our descriptive statistics. It's telling us here are our 2 groups, parents who are married. We have 10 people in that group. Their mean physical health score is a 79, standard deviation here of 9.72, and standard error of the mean. And then our second group, parents who are going through divorce. Again, we've got 10 people. Their mean physical health score was 68. Here's the standard deviation of 10.55 and standard error. And then below that comes out your independent samples t-test. You'll note that your independent samples t-test has 2 rows. It always will. One for equal variances assumed, one for equal variances not assumed. For this class, we will always be looking at the equal variances assumed row, which is always the top row, and you can ignore the bottom row. Okay, we won't go into that. That's a little more complicated and would be for another statistics class if you go on and take more classes in stats. So looking at this top row, The other thing you have to remember is this Levene's test for equality of variances. We are going to ignore that as well. That has to do with which row, and for us it's just going to be safe to always use equal variances assume and ignore this Levene's test for equality of variances. Okay? So then we're up here at the top row. Here's our T that SPSS computes for us. Here's our degrees of freedom. In this case, degrees of freedom is number of participants in both groups, which would be 20, minus 2. That gives us 18. Here's our significance. This is what we're looking at. We're comparing this to the 0.05 significance level. So if I said, is this significant at the 0.05 level? Well, 0.026 is less than 0.05. So this is statistically significant. The mean difference here is just taking 79 minus 68, the physical health score for group 1 minus the physical health score for group 2. It tells us we've got an 11-point difference. And the rest we can kind of ignore. So our statistical conclusion, what are we going to do? We're going to reject the null hypothesis because our obtained P of 0.026, remember that's coming from right here, is less than our critical P of 0.05. Saying your results in words, children whose parents are married have statistically significantly higher physical health score with a mean of 79 and a standard deviation of 9.72, and that's coming right here from your descriptive statistics, compared to children whose parents are going through divorce. They had a mean of 68, standard deviation of 10.55. Again, that's coming from right here, 68, 10.55. And then your T with 18 degrees of freedom is 2.43, right here, 2.43, 18 degrees of freedom. P is equal to 0.026. So that would be the way you write up those results. Very similar to what we've done in the past couple of weeks. I do want to mention one thing here, is that in your problem on a test or a final project, I will say to you, please test this at the point P equals 0.05 level. The other option would be to say, I want you to test this at the P equals 0.01 level. If I said to test it at 0.01, then your significance level would have to be less than 0.01. And if I said to do that on in this test, is this less than 0.01? It's not, right? 0.02 is greater than 0.01. So if I had asked you to test this at the 0.01 level, then I would say that instead of rejecting the null, we would actually accept the null, because our obtained P of 0.026 is greater than the critical P of 0.01. And substantively, we would say there is no statistically significant difference in physical health score. For children whose parents are married, you would give the same data, compared to children whose parents are going through divorce, and you'd give this data. T with 18 degrees of freedom is equal to 2.43, none of that changed. And here you would just say P is greater than 0.01. So depending on the statistical, the level that you're testing this at, if it's at 0.05, this is statistically significant. And remember, if we're testing it at an alpha is 0.05 level, we're saying we only want a 5% chance of making a type 1 error on this statistical test. And if we tested at the 0.01 level, then I would be saying we only want a 1% chance of making a type 1 error. We actually are making it harder for ourselves to make an error, a type 1 error. So that's important, and you're basically always going to compare the significance to whatever alpha level I give you. And I will tell you, test this at 0.05 or test this at 0.01. All right, so then you can go ahead and When you're ready, watch the next lecture on running an independent samples t-test. Thank you.